Very good morning to everyone. We will start the inauguration within a few minutes. Very pleasant morning to everyone gathered here. We will start the inauguration function within a few minutes.
Good morning. Sir, good morning, sir. Am I audible?
Good morning, sir. Audible, sir.
Okay. Just 2 minutes, sir. We'll start.
Yeah, okay, sir.
Yes, sir. Sir? Good morning.
Sir, yes, sir. Good morning, sir.
Yeah, can we start, sir? Can we start?
Yes, sir. Yes, we will
Yes,
start.
sir. We will start, sir.
Yeah.
Very good morning to everyone gathered here. I'd like to welcome all the participants for a AICT-sponsored 2 weeks online faculty development program on emerging trends and challenges in a VLSI mixed signal processing for fourth industrial revolution. Organizing by the Department of Electronics and Communication Engineering, Kongunadu College of Engineering and Technology. Welcome you all. Sunshine is a welcome thing. It brings a lot of brightness. In this way, now I'd like to call upon Dr. M. Dharmalingam, HOD of EC Department, to inaugurate this FDP. Please, sir.
Very good morning to all for this third phase, emerging trends and challenges in VLSI mixed signal. Our heartfelt thanks to AICT for giving this opportunity to our college. Bhaskar, audible?
Yes, sir. You are audible, sir.
Audible, sir. Yes.
Yes.
So this is the last phase. We already planned for 3 phases. So now 2 phases completed. So this is the third phase. So I'm very happy to welcome all the participants. And today's resource person, he's the first person he accepting our invitation from the phase 1 onwards. I'm really very happy to welcome Dr. S. Kumaravel, professor from Department of Micro and Nano Electronics, School of Electronics Engineering, EIT University, Vellore. So, welcome you, sir.
Thank you, sir. Thanks for your invitation.
Yes, sir. So, before going to start this today's session, a small introduction about today's resource person. Then the instructions and the procedures for attending this FTTP is given by our organizing team. Then we will proceed. Bhaskar?
Yes, sir. If your actions inspire others to dream more, learn more, do more, become more, you are a leader. I'm saying about the person who is none other than our today's resource person, Dr. S. Kumaravel, Associate Professor, Department of Micro Nano Electronics, School of Electronics Engineering, VIT University, Vellore. I feel overjoyed to welcome and introduce today's resource person, Dr. S. Kumaravel. He did his bachelor's degree from a Government College of Technology, Coimbatore, and postgraduate degree from a SRM Eastwari Engineering College in VLSI design, and also completed his doctorate in NIT Trichy. He worked as an associate professor at VIT, and presently he is the head of the Department of Micro Nano Electronics at VIT University. He also has experience as a maintenance engineer, junior research officer, lab engineer, and research associate. He is very much interested in mixed signal circuit design, RFIC design, low power VLSI design. He successfully fabricated ICs. He also published papers and his research work in IEEE conferences. I hope this session will be fascinating for you. Let me hand over the session to our resource person, Dr. S. Kumaravel. Please, sir.
Yes. Good morning, all. So I take this opportunity to thank the management and the faculty members associated with Department of Electronics and Communication Engineering to take forward a step to conduct this online short-term training program on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. And I'm highly obliged to Professor Dharmalingam, who is head of department in Department of Electronics and Communication Engineering, for inviting me as a resource person for the third time. So with this note, I would like to start upon the presentation. So I'll share my screen. Is my screen visible?
Yes, sir, visible, sir.
So the topic of today's discussion is going to be CMOS amplifiers for biomedical application. So as the application chosen is going to be biomedical application, we can understand that the signals that we are going to acquire from human is going to be in physical in nature, analog in nature. So those signal has to be converted into digital signal. So the concept become mixed signal processing. Okay, so I am going to talk about only on the analog front-end modules. Fine, digital modules I am not going to talk. In analog modules, how we can work upon to achieve a required specification for a certain biomedical application. So to go up with the discussion, the first slide I would like to mention that what is the difference between analog and digital. In today's trend, most of our Indian electronics engineers are inclined towards digital, whereas only very few people are working in analog. Why? Because analog IC design is complex and we need a strong background in physics, electronics, information and control theory, signal processing, communications. And analog IC design has got a variety of state-of-the-art solution, and it is highly dependent on technology, and we should have a strong background on modeling skills. And the electronic design automation tools used for building up these analog circuits are quite complex, but still we need this analog. We can't omit this analog unless and otherwise the signals that is available in the environment or in any source is going to be digital. Analog is going to be there. So let's take a quick example of our mobile phone, which has got plenty of analog circuits, RF circuits and digital circuits. I have taken up this slide from Professor Francesc Sarah Garrelets, Department of Microelectronic Systems, University of Barcelona. So if you look upon the circle, the outer circle is going to be mentioning like power supply voltage, transducers, and communication. Okay, so how we can interface all these three things? Okay, so in that perspective, if you see, we need a lot of analog blocks. So for communication, we require RF front-end blocks like low noise amplifier, LNA, mixer, power amplifier, voltage controlled oscillator, PLL, phase lock, low. And in analog domain, we require reference circuits, power management circuits, preamplifier, digital to analog converter, analog to digital converter, automatic gain controller, filter. The inner circle has got microprocessor, microcontroller, FPGA, DSP, and memory. So if you observe closely on this diagram, you will understand that there are a lot of analog and RF front-end blocks are involved in order to design this mobile phone motherboard or PCB, whatever it may be. Okay, so there comes mixed signal. So that means mobile phone is a mixed signal system. Okay, with mobile phone now we can interface any sensors or any signal that has to be processed. There are a lot of apps, real-time apps. Say for example, Ola. Okay, if you want to book a call taxi, you can use that app and you can book that taxi and you can go out, right? Similarly, there are a lot of apps are involved. Those apps you can install it in your mobile phone and you can do as you wish. Okay, but at the back end, these ICs are playing a major role. Okay, and why analog is complex? The reason is we are going to have a discussion on Mosfet based amplifier. Okay, so if you want to use those Mosfets in digital circuits, you can think it like a switch, either on or off switch. This is the only one realization when you think of using MOSFET in digital. Whereas in analog, you will have n number of components. You can think about that this circuit can be act as a resistor, it can be act as a current source, it can act as a diode, variable capacitor, just a capacitor, dependent current source, right? And then it can also act as a switch. So n number of realization can be observed for a single MOSFET when you use it for analog circuits. Okay, so that's why the analog system is complex. Okay, and we know the basics of MOSFET. It has got three regions of operation, three region of operation. One is cutoff, linear, and saturation. So we have got the drain current expression for these three regions of operation. Here ID is approximately equal to 0. That means which is the MOSFET is never turned on. For linear region and saturation region, this basic expression I think everybody knows. So this is of linear region and this is going to be in saturation region. Okay, so the current characteristics is shown over there. And for analog circuits, we are very much interested in this region of operation, that is saturation region. Okay. So this, I'm not going to touch upon these very basic circuits. Everybody would have know about this drain current expressions of MOSFETs. And MOSFET suffers from second order effects, namely channel length modulation and body effect. Channel length modulation and body effect. Okay, body effect in the sense, if two transistors are stacked one above the other, M1 and M2, here also the bulk is going to be there, VSB equal to 0 for M1 transistor. Whereas here, VSB is not equal to 0. So it suffers from body effect. Okay. So channel length modulation, due to channel length modulation, 1 plus lambda VD. Yes, the channel gets depleted from the drain, due to which the channel length is going to get decreased. Right. So these are all the things. And for our topic of discussion, we are mostly bothered about the region of operation is saturation region. In saturation region, how the small signal equivalent circuit can be drawn. So this is a high frequency model of MOSFET. Okay, so let's try to figure out how these capacitances came into existence. So if you take a MOSFET structure, substrate, NMOS, okay, N plus diffusion, gate, source, drain, bulk. Bulk is nothing but P substrate. Okay, so here you observe that there is a overlap between gate and the source. Here also gate and drain. Okay, so this is nothing. How a capacitance is formed? Two parallel plates separated by an insulating medium. Two parallel plates with dissimilar charges. Okay, with dissimilar charges separated by an insulating medium is going to form a capacitor. Similarly, here gate. Here we will have positive. Okay, positive potential we are going. Here N plus diffusion. Here you are having electrons. Okay, so this is SiO2. So it is separated by a insulating medium, which is SiO2. So this forms a capacitance CGS. So here CGS. Similarly here CGD. Okay, so CGS and CGD. Similarly, this is P and N junction. Here there is a P substrate and an N plus junction. So it forms a PN junction. These PN junctions are reverse biased. Your bulk will be connected to the lowest potential. Compared to other terminals. So this is going to be like ground, means here just a little bit of higher voltage will be there. So this is going to be in a reverse bias, these diodes. So we know in reverse bias, a depletion capacitance is going to be formed. We'll exit a depletion capacitance. Right, so this depletion capacitance we will name it like CSB and CDB. So this four capacitances is going to exist in a MOSFET. Bulk, drain, gate, source. CGS, CGT, CDB, and CSB. So this capacitances we are going to include it in our small signal model. Generally, in small signal model, we'll have low frequency model and high frequency model. At low frequency, how the equivalent circuit. So we know that we are going to apply a small signal V in, so through which the current is going to flow Gm times of VGS, and channel due to channel length modulation or not. So this is the small signal. If body effect is taken into consideration, then we will have GMB BPS. Okay. Right. So this is a low frequency model. So if you want to have the high frequency model, then capacitance comes into effect, because the capacitive impedance is given by 1 by omega C. If omega increases, this is going to get decrease. So it may affect the performance of the system. So we need to include for high frequency. For high frequency, CGS, CGD, and then here if you are going to have our bulk terminal, CSB, CDB. Okay, so these are all high frequency model of the MOSFET. The capacitance will come into existence in high frequency. So based on this, now we are going to understand how we are going to design amplifiers. Okay, so to have an understanding on the MOSFET amplifiers, let me start with the single stage amplifiers, some basics, then we will move with the high-end research concepts. So using MOS, we can design common source, common drain, and common gate. These are all the very basic topologies that we can build from MOS transistors. Okay, using this basic configuration, in order to design high gain amplifiers, we can go with Cascade Amplifiers and Cascade Amplifiers. Okay, Cascade Amplifier means common source, common source. Cascade means common source, common gate. So here we can write this as CG, CD, then CS. Okay. So using this amplifiers, we can design a very high gain amplifier. So we'll go with the common source amplifier with a resistive low. RD, VDD, M1 transistor. So bulk I am going to ground it always. For NMOS, the bulk will be connected to ground, and for PMOS, it will be connected to VDD. Okay, so now we need to determine the gain. This V in it denotes VDC plus small signal. Similarly, V out also it has got some DC quantity plus AC quantity. Okay, and this is DC. This is AC. And we have to bias these transistors in saturation region. So we can draw the circuit: gate, drain, common source. This is a common source configuration. Why we say it like common source means for small signal, source will be grounded. Okay, so this is source. This is going to be grounded. And from drain to source, there will be a current source. GM times of VGS. Here VGS is nothing but V in. Okay, and then if you take R0 into account, this will be V out, and here RD. So for small signal, this VDD has to be grounded. Okay, so we know of in small signal, DC source, DC voltage source needs to be grounded, and DC current source needs to be open circuit. The reason why we are saying that this is needs to be grounded and this has to be, so DC voltage source, let's take so whatever the current that I am going to draw, my supply voltage has to be constant. See here VDD, I can draw 1 milliampere or 2 milliampere or 5 milliampere, some current, drain current, but my VDD is constant, right? So based on that one, whatever may be the current, the voltage remains constant. Okay, so now if you take a slope on this thing, so V1, I1, V2, I2. So slope y by x, V1 minus V2 by I1 minus I2. So V1 and V2 are 0. I1 and I2 may be different value, but so this is going to be 0. So this is nothing but R. R is equal to V by I, that is equal to 0. So resistance is 0 means implies short circuit. or grounded. Okay. Similarly, for DC current source, whatever may be the voltage, my current remains constant. So I am going to take the slope of it, I1, V1. So I1 minus I2 by V1 minus V2. So this is going to be 0 by V, right? So it's going to be like 0. So resistance is nothing but V by I, right? Here, if you see this one, it is like 1 by I by V. So I by V is nothing but 0. So R is equal to infinite. Implies open circuit. Okay, fine. So this is where we need to understand why it is open circuit and short circuit. So due to which this RD, this resistance terminal, one terminal connected to VDD, that we need to ground it, short circuit it. Okay, now V out by V in. So V out by V in, how we can write this current is going to flow from here, from ground. So V out is approximately equal to minus, since it's going to flow from lower potential to higher potential. So minus GM VGS, and R0 and RD are parallel. So VG is equal to V in, so minus GM V in, R0 parallel RD. So V out by V in equals minus GM R0 parallel RD. This is nothing but voltage gain. Okay, so this is going to be the voltage gain for the common source amplifier with resistive load. So once you have determined the gain, we have used small frequency, low frequency model. So frequency and then gain. So magnitude of gain. So this is nothing but GM R0 parallel RD. So whether your gain remains the same as frequency keeps on increasing, whether your gain remains the same whether the gain remains the same for all frequencies. Anybody? Whether the gain remains the same for all frequencies? It doesn't remain the same because we are going to have capacitances in our high frequency region, right? So that capacitance effect will be SEGS, CGD, then CDB plus CSB. So let me draw the capacitance. So here it is going to be CGD, CGS, CSB, and CdV. Here, if you observe this capacitance, both the plates are grounded. Okay, that means this capacitance doesn't exist. Okay, only the three capacitance will be existing. So those three capacitance I am going to take. Okay, fine. So here we need to analyze the amplifier performance by changing with respect to frequency. That is frequency response analysis. Okay, frequency. So we would have covered up the basics in control systems. Bode plot, which consists of a magnitude plot and phase plot. Right. So this Bode plot has been drawn for a transfer function. So what is transfer function? Laplace transform of output variable to Laplace transform of input variable with all initial conditions to be 0. This is a transfer function. So h of s, one transfer function. So the generalized transfer function, we can write h of s is equal to k to 1 plus s by omega z1 by 1 plus s by omega p1, 1 plus s by omega p2. Okay, this is a transfer function. So now we need to derive the transfer function for our common source amplifier with resistive load. So this K is low frequency gain. So this GMR0, this is low frequency gain, K. Okay, whereas omega Z1, these are all zero frequency, a frequency at which zero exists. Omega P1, P2 are pole frequencies. Okay, so in circuits, what constitute to a zero and what constitute to a pole? That one we should know. So in circuits, so if you look upon this thing, the common source amplifier in circuit, nodes contribute to poles. Okay, nodes contribute to the poles. So here RSS. So here there is going to be one node. What is node? What is node? Two or more elements meet at a point or junction is termed as node. Okay, So there are two nodes are there in this circuit. Fine. This is one node and this is the other node, two nodes. And this is going to contribute to pole. Okay. This pole frequency is given as omega P1 is approximately equal to inverse of the product of resistance and capacitance associated with that node. Okay, product of inverse of the product of resistance and capacitance associated with that node. Then similarly, what contributes to 0? What contributes to 0? So if there is a feed forward path from input to output, feed forward path that connects to output contribute to 0. Okay, this is going to contribute to a 0. So here there is one feed forward path, so a 0 is going to be there. So for circuit designers, if you want to derive the transfer function of this circuit, already we determined the low frequency gain to be GM R0 parallel RD minus. Okay. Now we need to calculate the pole frequencies and the 0 frequency. Okay. So let's try to figure out omega P1. This is RS. Okay. Omega P1 is approximately equal to 1 by RS into CGS, this capacitance, and CGD is there, right? CGS plus some CGD is going to be there. So time being some I'll write CGD of Miller. Okay. So 1 by RS into CGS plus CGD Miller. Similarly, at the output side, omega 1 by RD, the resistance that is associated with this node is RD, and the capacitance is CDB plus some CGD. So CGD Miller. Why I am terming it as Miller means, in order to make the circuit analysis to be much simpler, so we should adopt Miller's theorems to our circuit. So what Miller's theorem states is that if there is an impedance that is connected between two floating nodes, X and Y, an impedance that is connected between two floating nodes, X and Y, that can be segregated to X node, and it can be segregated to Y node, provided same current is going to flow. Okay, same current is going to flow. So now this is I current and here also I current. So we can write Vx minus Vy by Z is equal to Vx by Z1. Okay, so Vx, if you take common, 1 minus Vy by Vx. So Z1 equal to Z by 1 minus Vy by Vx. That is nothing but voltage gain, output by input. Okay. We'll write like that. Similarly, at Z2, That time Vy minus Vx by Z equal to, so Vy, if you take common, 1 minus Vx by Vy, so it is going to be Z2 equal to Z by 1 minus Vx by Vy, which is nothing but Z2 by Z by 1 minus 1 by AV. Okay, so we can segregate the impedance that is going to be associated with individual nodes. So if you are doing it so, this CGD, I am going to break. This CGD, I am going to break, that is going to be associated with gate and drain individually. Okay, so Z1, now let me figure out this CGD. Now CGD, I am going to CGD Miller. What is that CGD? If Z equal to 1 by SCGD, then Z1 equal to 1 by SCGD into 1 minus AV. Okay, the capacitance is going to be CGD into 1 minus AV. Similarly, for Z2 is equal to 1 by SCGD into 1 minus 1 by AV. So CGD into 1 minus 1 by AV. In frequency domain, we will write the capacitance impedance to be 1 by SCGD. Resistance remains the same, whereas inductance is SL and capacitance is 1 by SC. Based on that, that CGD is broken into two capacitance, Miller capacitance, that is going to be associated with gate and drain node. Here AV is nothing but, what is AV? AV is minus GM or not parallel. If you substitute over there, you will get CGD into 1 plus GM into R naught parallel RD. Here also CGD into 1 plus 1 by GM R naught parallel RD. Okay, let's put this as approximately equal to minus GM RD. So V in RS so earlier capacitances CGS GM times of V in R naught parallel RD in CDB. The CGD only, here we have got CGD but this CGD is Miller's theorem. Miller's theorem we are breaking, and this component will come as 1 plus GMRD CGD into 1 plus 1 by GMRD, because AV is equal to minus GMRD. So this part now it is omitted. Okay, so now we have to see. So how many nodes are there? 1, 2. So omega P1 will write 1 by RS. These two capacitances are in parallel. So CGS plus GM. Omega P2 is nothing but 1 by RD parallel R0 into CdV plus CGD into 1 plus 1 by GM RT. So this is the pole frequency. So now 0 is not there. Since we are removing 0 is Miller's theorem, 0 is neglected. Okay. So now we can write the transfer function H of S, that is V out of S by V in of S equals minus GM R0 parallel RD divided by 1 plus S by omega P1 to 1 plus S by omega P2. So you can substitute that 1 by omega P1. This is approximately equal to 1 by RS into capacitance at the source side. So here also 1 by RD into CD at the drain node. Okay, so now if you want to draw the Bode plot for this thing, right, it is going to be GM RD approximately. Then when omega is equal to omega P1, when omega is equal to omega P1, your gain starts rolling off. Okay, that means a pole is there means minus 20 dB. Minus 20 dB per decade. Then omega P2. Once omega P2 is there, then you will have minus 40 dB decay. So for this, the magnitude plot phi, already there is a phase shift of 180 degree. So we know in pole, a pole is introduced means 90 degree phase shift, right? So 90 degree phase shift exactly at the corner frequency will have 45 degree, and then 10 times of omega P1, 10 times of omega P1, another 45 degree. Okay, so we'll have like this. Then similarly omega P2 45 degree. Okay, 10 times of omega P2, another 45 degree. Okay, so you will have something like a smooth curve. Okay, so this is termed as unity gain bandwidth. From where we will draw a straight line. This is going to be where it touches that 5 degree. So 180 degree minus that 5 degree is going to be the phase margin. Okay, it gives the stability of the system. So generally it can range from 45 degree to 80 degree for the system to be stable. Okay, so this is how we will be plotting. So how we are going to do this thing means this is a two-pole second order system. second order system. Okay, in the denominator, 2 poles are there. Number of poles defines the order of system. Okay, so these are all the very basic throughput approach. So your gain doesn't remain constant even at high frequency. What causes this thing to be rolled off? What causes this thing to be rolled off? So let's take a simple single pole transfer function, A naught by 1 plus S by omega p. Okay, now I am going to take 20 log h of s is equal to 20 log magnitude of h of s, and by 20 log of, not magnitude, then magnitude of 1 plus s omega I can write as j omega by omega p. Okay, so for a complex number a plus ib magnitude, it's going to be square root of a square plus b square. Right? So here you can write 20 log of a naught square, that is going to be square root of a naught minus 20 log of, all right, square root of 1 plus omega by omega p whole square. So 20 log minus 20, that square root, I can write it as the square root. I can put it like half, right? So it is going to become 10 log of 1 plus omega by omega p square. Now when omega is equal to omega p, you get 20 log a naught minus 10 log of omega p. It becomes like 2, right? When omega is equal to omega p, both gets cancelled. So log 2 is 0.3010 minus 0.3010. So we'll have minus 3 dB. Okay, your gain drops by minus 3 dB exactly when omega is equal to omega p. When omega is equal to 10 times of omega p, we will have 20 log a naught minus 10 log of 10 omega, for which you are going to write omega p gets cancelled. So 101 you will get. Let's approximate like log 100. Okay, so 20 log a naught. Log 100 is what? 2. 10 into 2. So minus 20 dB per decade. That means a pole is going to be there, means per decade. This is per decade, 10 times. Okay, you will have minus 20 dB per decade. That's why here we are having per decade 10 times of. Okay, so these are all very basics that we should know. So with this thing as an introduction, now we will go to the slide. There are a lot of amplifier topologies with a single stage amplifier. In single stage amplifier, we will have noise. If noise is going to be there, VDD plus delta VN means at Vout also it suffers from noise. It suffers from noise. So to overcome this one, we will go with differential amplifier. Okay, so this is the differential amplifier, and this is of cascade configuration. This is of cascade. This of cascade configuration. So half circuit. Here, when you go with the differential amplifier, one thing we should remember that here we are applying differential mode signal. So differential mode signal means So differential mode signal. Two signals equal in amplitude and opposite in phase. This is termed as differential mode signal. That is, two signal equal in phase and equal in amplitude and opposite in phase. There is common mode signal also. Common mode signal means same signal is going to be applied to both the inputs. Either you can give like this or like this. Okay, same signal. Okay, this is differential. So with that one, here we are going to give. So when you go with this node will become like virtual ground. Virtual ground, because the current that is going to flow through M1 will be of this phase, and here from M2 of this phase. If you apply KCL at this node, two equal signals opposite in phase enter at this junction means it gets cancelled. So it becomes like virtual ground. Okay, so through virtual ground, now the half circuit we can draw like 1M3 VDD. So we need to identify how many nodes are there in the circuit. So here this is one node, this second node, and this is third node. So three nodes are there. The pole frequencies are written over here like this. The pole frequencies are given this. Okay, so now so far we have tried to understand how to derive the transfer function of an MOS amplifiers. Based on the transfer function, how we need to understand how the gain is getting changed for a range of frequencies, all those things. Now we'll go with the application, biomedical application. As we discussed, the biomedical signal frequency or ranging from few hertz to few kilohertz, that is up to 10 kilohertz. These are all the biomedical signal that can be acquired from a human body, and the amplitude of the signal, if you observe, is of very few millivolts amplitude, from nanovolts to few millivolts amplitude. Okay, fine. So we are going to process this signal. Okay, this signal 10 millivolt is input signal means we are going to process it, and we are going to have a digital display in the CRT display tube. All right. So what are all the measures we need to take for processing this signal? So biopotential signal, first stage is low noise instrumentation amplifier, then programmable gain amplifier, then filter, then ADC. So to acquire this biopotential signals and processing it, the front end block, low noise instrumentation amplifier, it should have 3 microvolt RMS, the noise voltage. Okay, and it should constitute only low power. Low power, and the gain of the amplifier should be somewhat greater than 50, and the bandwidth as a biopotential signal is less than 10 kilohertz. It can be. And since we are going to acquire the signal from the human body using electrode, that electrode will introduce an offset of 100 millivolt. So we should try to have an high pass filter characteristics to filter this offset. Okay, and it should have a high input impedance, high CMRR, common mode rejection ratio, power supply rejection ratio, and it should have high dynamic range. So these are all the characteristics that we should look into it for designing this instrumentation amplifier in order to process this biopotential signal. So now, as we discussed, this is highly dependent on technology, right? I have said that it is highly dependent from technology, right? As technology varies, it will have the impact. So impact of CMOS scaling on analog design. If you have the scaling of technology leads to higher level of integration, and FT of the mass device increases. Whereas in demerits is signal to noise ratio is decreasing, and intrinsic gain. This is very, very important parameter. Intrinsic gain steadily reduced with gate length. That means it is getting reduced. So scaling of voltage leads to increase in why? Because the gain is AV equal to GM or not generally. Okay, GM or not. This is getting reduced means. So if you are going to realize it in 180 nanometer technology, this one in 90 nanometer technology, still it is going to be lesser means same expression, but this is going to be reduced means we need to burn more power. Okay, so scaling of voltage leads to increase in power consumption. What I try to mean is in digital circuit, P is equal to CVDD square F. So technology scales down. Technology scales down, VDD scales down. So power is going to scale down. Whereas in analog, GM or not, this parameter is decreasing as technology scales down. Okay, so if you want to design high gain, we need to burn more power. To achieve the same gain in lower technologies, deep submicron technologies, we need to burn more power. Okay, and moreover, VDD, this is a supply voltage, signal to noise ratio. Decreases, SNR, S by N. Signal is getting reduced. It should VDD is reduced, no? So signal level also is going to reduce, so it gets decreased. So in ADC, SNR equal to 6.02 N plus 1.76. So if SNR is decreasing, N is going to decrease. High resolution we will not achieve. It's not possible. These are all the demerits we are having for analog design. Okay, so to overcome that one, how we can go for it. So this is an instrumentation amplifier, and this is the block we are going to design. So we used to call this as GM block. The transfer function is given as C in by CF into 1 plus S CLC. In this, again, I am not going to involve in designing the transfer function of the complete circuit diagram. So let me just give you an idea that it should have an high pass filter characteristic. That's what we have seen, high pass filter characteristic. Okay, and it should have a low bandwidth, low pass characteristics also. So this is at the new denominator. This is a low pass filter, and this is a high pass filter. Okay, fine. So the bandwidth here, this is a low pass filter 1 by 2 by GM AV naught by CL, and high pass filter is SRF CF 1 plus SRF CF. Okay, so here the gain is dependent on the input capacitance and the feedback capacitance C in by CF. This is the low frequency gain. Okay, so to realize this GM block, we are having cascade amplifiers, telescopic cascade and folded cascade. Telescopic cascade and folded cascade amplifiers we are having. So these are all the major topologies for designing high gain amplifier. Designing high gain amplifier. So I am going to derive the high gain derivation for this circuit, folded cascade. Okay. So let's try to figure out this one. Generally, AV is equal to GM into R out. This GM is nothing but I out by V. Okay, so that is going to be GM1 and R out is GM7 or not 7. So let's try to figure out how we can derive this for the folded cascade. We call OTA, folded cascade operational transconductance amplifier. So for this folded cascade operational transconductance amplifier, the topology I'm going with half circuit. Let me go with the half circuit so that so this is a folded cascade amplifier. So when you apply differential signal, this node is going to become virtual ground. Okay, then we can go with the half circuit. So half circuit, if I go V in M1, this is going to be ground. M1 source is ground, right? Virtual ground. Then here I'm having M3. M5. So this is the half circuit. Right here we are going to take V out. So to determine the gain AV into GM into R out. So to find GM, now we are going to apply two lemmas. Okay. So to find GM, short circuit the output node, apply test signal at input. So how it will come? M1 you will have input. This is the test signal. Mean this is VB3, this is M3 PDD. This is M5. This is where the output node. This is grounded. If you observe here, output M5 output, I am going to ground it. I have grounded. Now for small signal, this has to be grounded. This has to be grounded, and this has to be grounded. So everything has to be grounded. Okay. So here if you see VSG, this is a PMOS type, VSG equals to 0. Okay, if VGS is 0, in a small signal, the current that is going to flow, GM times V in. If V in equal to VGS, this current source will not be there, just R0 alone will be there. The resistance alone will be there. So I can draw this M3 as R0 3. That is going to be grounded. Okay. And then V in, this is going to be M1. This is going to be I out. I out current is going to flow. Right here, I out from drain to this is drain and this source. I out current. Okay, I out current is going to. So this I out current is going to flow through this M1 transistor itself. Okay, this is high impedance. So I out is equal to, this is flowing from the ground. So minus GM1. So I out by V in equal to minus GM1. GM is nothing but ratio of the output current to the input voltage. This is going to be GM1. So for the gain AV, GM into R out, GM is nothing but minus GM1. R out, we need to determine R out. So to find R out, short circuit the input and apply test signal at output. So now we are going to short circuit the input, apply a test signal, right? So let's try to so I'm going to short circuit this one. And I'm applying test signal. Okay, so this current IX, it's going to get divided like this one, right? I1 and I2. So IX is equal to I1 plus I2. So I have to determine R out. R out is Vx by Ix. This is nothing but the impedance R down, and this is going to be like R up. So I can write R up parallel R down. Okay, parallel combination of this thing. So let me calculate R down first. So M7 and M9, this is the transistor number. right? So this is going to be VB4, VB1, this is M7, M9, and here we are going to apply the test signal as Vx, and that is the current that is going to flow. Ix first we are taking, right? Here the small signal VGS equals to 0. So the circuit becomes R09. The equivalent circuit becomes R09. And this is M7. VB is grounded. Vx, Ix. So now draw the equivalent circuit, right? So this is the gate of M7, G7 grounded. And source 7, this is source 7. So GM, VGS 7, R0 7, R0 9. Okay, here VGS 7, how we can write? VGS 7 equal to VG7 minus VS7. VG7 is ground, 0 minus VS7. That means VGS7 equal to minus VS7. So I can, in order to remove this negation, I am changing the direction of current like this. So GM VS7. Okay, so now I am going to apply KVL along this path. KVL. Okay, from this ground to this ground. So Vx is equal to the drop across R07. Drop across R07 is what? Ix plus GM7. GM Vs7 into R07 plus Ix into R09. What is Vs7? What is Vs7? Vs7 is nothing but Ix into R09. So Ix plus GM7. I will write GM7. R09 R07 plus Ix into RO9. So Ix, if you take common, we get R07 plus GM7 R07 R09 plus R09. Okay, now Vx by Ix is equal to R07 plus GM7 R07 plus R09, which is approximately his. Okay, so R down is this one. Here this GM7. So what we can understand is this is cascode. This acts as a cascode device, and this is input device. So for this configuration, the intrinsic gain of the cascode device GM7 or not 7, intrinsic gain, intrinsic gain of cascode device into output impedance of input device. Do you follow? GM7 R07 R09. Similarly, looking upward. Here this VGS is 0 and this VGS is 0. Only from this node, we can just looking M5. So R not what? this is where this configuration are up. Okay, here both the VGS is 0, so R01 from this node to ground, R03, and this is going to be R01. Both will be parallel. This is M5. So you will write R up is equal to GM5 R05 into R01 parallel R03. So this is the total output impedance. R up and R down we have determined. So the impedance is going to be GM7 R07 parallel R09G. So this is the voltage gain. Okay, so how many nodes are there in the circuit? We need to identify. So how many nodes are there in this circuit? Here we are having here node 1, here 2. This is like cascade node. And this is output node. So we should determine the pole frequencies. So the pole frequency is given as omega 1 by R out into CL and omega P2 equal to 1 by R2 C2. So replace it with the high frequency model of the Mosfet and you will get all those things. So this is the with respect to gain and frequency response analysis. Now coming to the noise analysis, this is the Mosfet noise analysis characteristics. So thermal noise, it's nothing but the white noise, and this is going to be flicker noise. So low frequency noise is low frequency flicker noise, high frequency thermal noise. Okay, so the expression of the noise equations are given like this. Thermal noise means Vn square bar equal to 4kT into gamma by Gm. Flicker noise similarly, K by Cox into 1 by WA into 1 by F. Flicker noise. So generally, if you for flicker noise, if you want to low flicker noise, PMOS is suitable because mobility of electrons is much greater than mobility of holes. Okay, mobility of electron is much greater than mobility, or 2 to 3 times of mu p. Okay, in that case means if same current only has to flow, this is NMOS, I current, PMOS, high current has to flow means the device size for the PMOS, it should be 3 times of W by L of M1. Let's take this is going to be M1 and M2. So what happens? The device size is going to be 3 times of W. So 3 times if it is going to be increased, okay, 3 times W, the flicker noise is going to get decreased. That's why PMOS device is more suitable. Okay, and one more thing, if you want to reduce the noise, GM is inversely proportional. The noise is inversely proportional to GM. So if GM can be increased, the noise is going to get decreased. Okay, so we are identifying topologies how to increase the GM so that the noise will be reduced, so that we can achieve it for the biomedical application where the noise is very, we need to design the noise. It should be less than 3 microvolt RMS. Okay, so we are going with the topology. So for a noise signal, how these are all there, I'm not going with this thing. For resistor, the thermal noise is given as 4 kT R. Okay, so let's try to figure it out. The thermal noise final expression so that you can understand. So this is the thermal noise, input referred thermal noise GM. GM is increased means thermal noise is going to get decreased. So we need to identify the topology for which the GM is high. So with that as an example, from the folded cascode OTA. So here we are going with PMOS type. This is the PMOS type folded cascode amplifier. So there is a literature in the recycling folded cascode OTA, recycling folded cascode. Here what we does is to improve GM. To improve GM for the same power consumption, this M1 is split as M1A, M1B. M2 is split as M2A and M2B. Similarly, M3 is split as M3A, M3B, M4, M4A, and M4B. Okay, remaining all remains the same. So when we go with this configuration, the GM is enhanced by K plus 1 times. GM is enhanced. Okay, so if GM is enhanced, the noise is going to get reduced. The noise is going to be reduced. So in literature, lot of topologies are there. Here also improved recycling folded cascode OTA. Here further, we are adding one more additional path compared to the recycling folded cascode. Here we are adding one more path, due to which the GM is increased by a factor of K by A plus 1. So our ultimate motive to design low noise amplifier is the GM should be very high, so that GM should be very high to minimize the noise. This is the most important factor in low noise amplifier. Okay, so apart from that, now this GM alone, minimization alone is not the only problem to only solution to reduce the noise. And moreover, there are topologies where source degeneration, negative feedback. If you could include negative feedback, then also noise is reduced. So for the folded cascode amplifier, we are giving negative feedback over here, source degenerate, whichever the transistor that doesn't contribute to GM. Okay, transistors that doesn't contribute to GM, source degeneration can be adopted. So M3, M4, this R3, R4 are source degeneration. So what does it mean is GM by 1 plus GM RS. That means this transistor GM 4kT gamma GM is a current IN square bar equal to 4kT gamma GM. This GM has to be minimized, the current noise. So GM by 1 plus GM RS it will come. So source degeneration. So like this, people have adopted many techniques. Okay, again for the recycling folded cascode, they have adopted the source degeneration technique with some ratio of current that is going to flow. Thereby, the noise is reduced. This is my research topic. So I have adopted for improved recycling folded cascode the source degeneration resistance. I have given the, so that the noise is further reduced. So the noise equation is given there. So here the device sizes are chosen to be 240 by L. These are all in subthreshold region. We will have more GM. Generally for the transistor in subthreshold region, more GM will be there. Okay, GM is equal to ID by VT. This is thermal voltage compared to other regions. So we will bias the input transistors in subthreshold region so that the noise will be very minimal. So here, if you observe everywhere, the input transistors are PMOS. These are all PMOS. So flicker noise can be reduced. So generally for biomedical applications, the input transistor should be of PMOS device, because flicker noise is of low frequency. Okay, so the device size, and we are which are the transistors that contributes to the total noise contribution. So for a biomedical application, the low noise amplifier can be analyzed with respect to noise efficiency factor. This noise efficiency factor should be minimum, so that it defines that the designed amplifier is good for biomedical application. Power efficiency factor also should be minimum. So based on that, if you observe here, my work, I have for the same power consumption 1.5 microwatt of power. The noise I am getting is 2.0. Maybe the bandwidth may vary. Within this band for our biomedical application is 10 kilohertz. Okay, anyway up to 13.6 kilohertz I have done. It is 2.99 microvolt RMS. So we want the noise to be less than 3 microvolt RMS. So whereas if you observe here, the first paper 80 microwatt of power, here it is only 1.5 microwatt of power. Okay, so we need to characterize this amplifier, design this amplifier by taking noise into consideration and gain also into consideration. So with this thing, I think what are all the parameters that you should give importance while designing the amplifier for biomedical applications. Okay, so these are all the references. So the paper which is very, very important for startup with the biomedical application, the amplifier designs. So I request the participants, you can go with the GMBID with this textbook, and then Rahul Satpeshkar, Batana Panage. This is a very basic paper. Then I have compared for my research work these papers. So Batana Panage, Chengya. Okay, during my research time. Remaining all things we are referring it, but we need to identify the work that we are going to carry forward. Based on that, okay, so with this thing I'm ending this. If any queries, maybe you can ask me on this topic, please. If any queries.
Dear participants, this is the time for question and answer session. If you have any doubts or queries, you can ask now. You can either post your question in chat box or else unmute yourself and discuss with our resource person. Your mic is enabled now. Sir, there is one question in chat box.
Yeah, why P-type is used in biomedical applications? Because in PMOS, the mobility of holes is very less compared to NMOS device. So if you want to design the amplifier for the same current, just show you an example. So in M5, this is PMOS device, right? Same current only has to flow. Same current only has to flow means both are in saturation region. ID is equal to half mu n Cox W by L VGS minus VTH whole square. Right? For PMOS, again, this is for NMOS. For PMOS IDP, we can write half mu P Cox W by L VGS minus magnitude of VTH whole square. So mu n is much greater than mu p. So same current only has to flow means mu p is lesser means to map it with, we are going to give 3 times, 2 to 3 times. Your mobility of electrons is going to be higher than the mobility of holes. So to map it with, we will go with larger device. When you go with larger device, the flicker noise W Here, this is flicker noise expression. W is increasing. Okay, for the PMOS, if you go W is increasing means this is going to get reduced. The flicker noise contribution is going to get reduced. Flicker noise here. W is increasing means this is going to get reduced. That's why PMOS device, we will always go with PMOS device as input for biomedical application. Is it clear? Is it clear? Any other queries? Any other queries? Okay. Sir? Hello?
Yes, sir. I think there is no more queries from participant side, sir.
Yeah. So,
Let me wind up the session, sir.
yeah, let me wind. So, thanks for the opportunity that has been given to me to deliver my expertise. And I thank the participants for attending this lecture. I hope you would have got an idea how to start up with designing amplifiers for biomedical applications. So I have given you enough topics that has to be covered while you are going for designing it. Thank you. Thank you all.
Thank you very much, sir, for your nice presentation. Thank you, sir.
Yeah. Yeah. So shall I leave, sir?
Okay, sir. You can leave now, sir.
Okay. Thank you. Thank you, sir.
Thank you, sir.
Participants, now I go to give you some instructions about this FTP. At the end of each section, we are going to post a attendance and a feedback link. You need to get a 80% of attendance to get a certificate. And at the last session, we have one MCQ test, and based on that MCQ exam percentage and attendance, you will get a e-certificate. Participants, now the day 1 session 1 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. And one more instruction, while filling the feedback form, kindly select your respective FTP ID. That FTP ID document is already sent through the WhatsApp group, and now also I go to post in this chat box. Kindly check it. The FTP ID document is attached in the chat box. Kindly check it. The attendance and the feedback link for this day 1 session 1 is posted in chat box. Kindly fill it soon. And all the participants are requested to join the afternoon session at 2 p.m. sharply. Thank you all.